In physics and mathematics, phase space is a key construct that is used to represent the complete picture of a physical system. Unlike position space or momentum space, where only partial information about the state of the system is represented. So, in this video, I'm briefly going to explain the concept and why it is useful to represent a complete picture in classical mechanics. And then at the end, I'll briefly talk about how the picture is extended to quantum mechanics. So, let's dive deeper into this. And as a reference, let me start with position space because that is the most familiar to most students. So position space is a three-dimensional space with xyz as coordinate, and a point here represents the physical position of the particle. I'm assuming that we have a single particle that we are talking about. And similarly, we can have a momentum space where we represent the momentum of a particle using the three-dimensional coordinate system. So a point here would tell us how the particle is moving. So position space tell us where the particle is, and the momentum space tell us how the particle is moving. On the other hand, the phase space combines these two descriptions into a six-dimensional coordinate system where the axes are both position and momentum, and they're all treated equally. So if there is a point here, this represents both its position and momentum. It's a point has six coordinates: x, y, z, px, py, pc. So as the time passes, this point moves in this space because in general its position and momentum can change. So the dynamics is represented by a trajectory in the phase space. So this represents the complete picture of this particle. This concept is especially useful in statistical mechanics, where in statistical mechanics, suppose we have a system with n particles. So if there are n particles, then we can represent in a 6n dimensional phase space. So phase space would be 6n dimensional phase space. So a particle here would have 3n coordinate for position and 3n coordinates for momentum. Now suppose at one instant of time in this box, the particles have some definite position and momentum, so that would correspond to this single point. And if one or more particle change position or momentum, then it would correspond to another point in the position space, and so on. So each point represents the complete state of this system, not just of a single particle, but this point represents the state of all the particles combined with this single point in this phase space, because this is 6n dimensional. So 6 dimension for each of particle, and if there are n particle here in this box, so these 6n coordinates will represent the state of each particle in this position space, in this phase space. Now let's briefly talk about what happens when we go to quantum mechanics. So in quantum mechanics, we know that definite position and momentum cannot be simultaneously assigned to particle because of the Heisenberg uncertainty principle. So this is proportional to Planck's constant. So this concept of phase space can be easily extended if instead of representing these line trajectories, we use smeared out sort of probability distribution of particles. So as an example, suppose this is the phase space for, let me just take a single particle. So for a single particle, there are three position coordinate and three momentum coordinate. So for example, for a ground state of a harmonic oscillator, there will be something like this blob, where if I draw it in two dimension, in one dimension, this would look like something like this. So there's a higher probability distribution in the center and lower probability distribution as we move around. So for example, what I can do, I can try to have a dense point here and then, a little bit less density here. So this is not like many points, it's like a single blob with uh, uh, spread out function in this position space. So this delta x and delta p, they sort of quantify the uncertainty in position. So here in the classical mechanics, the for example, if there is an oscillator that might represent a trajectory like an ellipse in this phase space, and here it would represent a blob like this, that its extent tells us the uncertainty in this position and momentum. So this concept then help us in statistical mechanics to define ensemble as well, that we can easily represent the ensembles of various systems in phase space, because we only need a single point to represent the state of all six n particles. So to summarize, uh, we can say that the phase space combines both the position space and momentum space into a single coordinate system, and then each point in the phase space for classical mechanics represents the definite position and momentum of all the particles in the given system. And in quantum mechanics, instead of a point and line trajectories, we have smeared out blobs that represent the uncertainty in the position and momentum of the systems.